Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, we're going to get started on lesson number 4. This lesson is entitled Investigating Proportional Relationships, and this is the very first lesson in 7th grade that's going to deal specifically with proportions. Now, I'm not going to teach you strategies for solving proportions today, other than just using some common sense in a situation where you'd be able to solve a proportional relationship type of problem without knowing any formulas, without being taught any specific strategy. Now, in order for us to do this lesson, we need to have some supplies first. So what I would like for you to get is a ruler that has centimeters on it. Hopefully you've got one somewhere around the house, and the centimeter ruler, most rulers have, let me go ahead and pull this guy up for a second. Most rulers have inches on one side, and then the smaller unit are the centimeters. So find a ruler that looks like this if you can. And the centimeters are not the little tiny ticks. Those are millimeters. Remember, the centimeters are like the 1 centimeter, 2 centimeter, 3, 4, 5. And you'll know you're measuring the centimeters when you see that there are 5 centimeters pretty close to 5 centimeters for 2 inches. So if you're measuring on this side, you're going to get the measurements wrong. So centimeter ruler, make sure you're measuring the centimeters. And pennies. You don't need a ton of pennies. At least 10. 10 will work. If you have 20, 30, 40, you can do that as well. You can get as many pennies as you can find, but a minimum of 10. Try and find 10 of them, okay? So what we would do here for this lesson, let me get rid of that too, is first thing I like to do is have groups predict how many pennies. No, let me change that. How tall would a million penny tower be? Okay, so if you stacked up 1 million pennies, one on top of the other, how tall would it go? And then we would have teams, groups of like 3 or 4 predicting. And in the past, people would say, oh, that's going to be like 200 centimeters. And other people are like, no way, it's going to be 200 meters. And other people are like, no way, that's going to be like 500 kilometers, which would take you into outer space. So a lot of times the predictions are all over the place. What I'd like for you to do is just think about how thick 1 penny is. And if you were to stack them, how tall would it go for you to have 1 million pennies? Just, it can be a wild guess, or it can be an educated guess. See if you can think of that and jot it down. All right, so there's a nice artist rendering of a million, or at least a tower of pennies. I don't know how many are in there. All right, so let's read through the intro. Can you imagine a tower built out of 1 million pennies? How tall would it be? In this lesson, you will work with your team or on your own to predict just how tall such a tower would be. To make sense of this question, you will measure some pennies and investigate the relationship between the height of a tower of pennies and a number of pennies in that tower. This is an example of a special relationship called a proportional relationship, which you will learn much more about later in this course throughout the year. So here's the question. How tall would a tower of million pennies be? Would it be taller than your school building? Taller than your house? As tall as Mount Everest? Mount Everest is like 29,000 feet, which is almost 9,000 meters. Remember, we're not dealing with feet or inches, we're dealing with centimeters, meters, and kilometers, which this, by the way, is 8.848 kilometers. So, somewhere between 5 and 10 miles. It's kind of tall. So, discuss these questions or think about it on your own and make your prediction. Okay, so you've hopefully made your prediction. Now what I would like for you to do is I would like for you to create a table. On the left-hand side, we're going to put the height of the tower in centimeters. and then list out these numbers that you see here. The dot, dot, dot is just showing that you're going to have a gap. We're not counting by ones. We're skipping 5 here, we're skipping tens, and then so on and so forth. And then you're going to record the number of pennies. So you've got to make sure that you measure these accurately. So remember, you're getting a centimeter ruler. You're getting the centimeter side of it, not the inch side of it. Take a penny, and that's not what our pennies look like, but that's the only coin I could find on my program, and stack them as such, okay? And you are not measuring 10 pennies to find out how tall 10 pennies are. Right now, you're actually stacking the number of pennies so that you can get to 1 centimeter. So here, what's this? Looks like I have 4 of them, and of course, these are not real representations. So don't believe me that 4 of them would be exactly this on your ruler. But just stack them like this until you get to the 1 centimeter mark, and then to the 2 centimeter mark, and jot down, count how many there are, and then go to the 3 centimeter mark. And one thing I want you to be very, very careful of is this. A lot of times people think that you start at the edge of the ruler, but you can't do that. If you've got any kind of a gap like this ruler has, you've got to make sure that you start measuring them from the 0 line, which means you might need someone to hold the pennies while someone else at home holds the ruler to get those matched up perfectly, okay? So what I'd like for you to do is go ahead, make sure, if you haven't done it already, find that ruler, find some pennies, and start measuring. And you see how this says 5 centimeters, 10 centimeters. You probably don't have a ruler that has 20 centimeters or 30 centimeters. If you've got a meter stick, wonderful. You could do all of these and measure them, but you know, that can be kind of cumbersome with the pennies as well. So see if you can't come up with some kind of a strategy so you can fill out this entire table. Remember, you're writing down these measurements and you're finding the corresponding number of pennies. Go ahead and pause, and then come back when you've got everything filled in. Then we'll talk about these questions. All right, so let's assume you just did a fantastic job. Your table is written neatly and clearly in your journal, and you've got all these numbers written on the side. So it says, how many pennies does it take to build a tower that is 1 centimeter tall? All right, generally what I do here is I take a record of every single group. Remember on that first page how everyone made the predictions? Well, then I go back to each one of these teams and I have them actually report out how many pennies they each found for 1 centimeter. And the consensus is always 7 pennies. So 1 centimeter is equivalent to 7 pennies. So does it make sense that 2 centimeters would be twice the number of pennies? That is the nature of proportional relationships. There's a multiplier that's happening here. So as we work further down, 3 centimeters, 21 pennies, 4 centimeters, 28 pennies, and so on and so forth, until eventually you start to realize something here. You start to realize if 1 centimeter is equal to 7 pennies, what's the strategy? All we have to do is multiply the number of centimeters times 7, and that will give us the total number of pennies in those given towers. So what is 7 times 10? 70. What's 7 times 20? 140. 7 times 30? 210. 7 times 100 is 700. So this is how mathematicians, or people in different lines of work, maybe they don't have the measuring tape or the rulers to measure something that's really, really big. That's pretty much impossible to build, and probably like the 1,000,000 penny tower, that's pretty much impossible to build. But we could still use proportional reasoning to figure out how tall it is by doing an investigation similar to this. Okay, so hopefully you were able to figure out what these measurements were, and this was relatively intuitive for you. This intuitive process that was used is proportional reasoning. Oh, what happened? Stop it. Okay, so now Carol says, I have an idea. If I know how tall a tower of 100 pennies would be, maybe that could help me figure out how tall the tower of 1 million pennies would be. All right, so here we've got our the table. What I would like for you to do, so you don't have to build a new table, but where would that 100 be? That 100 might be somewhere around here, correct? Maybe I'll change the color of that. Let's change that to blue since we're going to go in a different direction. So the 100 mark could be right here, and the 200 mark could be right there, and maybe we could put the 50 mark in there. So if we multiplied the number of centimeters times 7 to give us the number of pennies in that type of a tower, what process needs to happen to go in the other direction? What's the opposite of multiplying? Well, if you said that we would, instead of multiply, we would divide by 7, then that would be the correct answer. So why don't you go ahead and see if you can figure out, instead of multiplying the number of centimeters times 7 to get the number of pennies, let's multiply the number, or I'm sorry, divide the number of pennies by 7 to figure out how tall this tower would be. So we set up the division problem. Instead of multiplying, we divide. So let's go ahead and work through this process. Never a bad idea to practice our division, even though we've got a nice calculator right down there. Oh, I just saw an answer. Okay, so the division process. We're always asking ourselves, what do you multiply times 7 to get 100 for an answer? And another way of looking at it is, how many 7s can you fit into the number 100? Well, rather than, I know we can fit like 10 of them, right? Because that would be 70, but can we fit 15? I'm not really sure. So we could do guessing and checking, but it would be better if we used the division algorithm. So with the algorithm, I just go one digit at a time in our dividend. How many 7s fit into the number 1? And the answer is 0. You can't fit 7 into 1. So let's move to the next digit, and that makes this 10. How many 7s fit into the number 10? Well, one of them, right? Because if you had 2 7s, that would be 14, and that would be too big. So we're going to take 1 times 7, and we'll subtract it from the 10, and that gives us 3, and then bring down the next digit. So now, how many 7s fit into 30? 7 times 3 is 21, 7 times 4 is 28, and 7 times 5 is 35. So we can't fit 5 of them, we can only fit 4. So 4, that was 28. Uh-oh, I'm running out of room here. Let's bring this down. Let's do a little subtraction. And it doesn't terminate, which means I need to add another digit here, correct? And we can keep going through this process. That's almost a 3, but not quite. It's going to be a 2, and then that's probably going to end up being like an 8 or a 9 over here. But we're not going to have a fraction of a penny. So, or actually, no, these are centimeters, aren't they? We could have decimals. At any rate, let's just round it off. This is very close to 14 centimeters. So that's what we're going to say. It's a little bit less, or a little bit more than 14, like 14.2, maybe rounds up to 14.3, but we'll call it 14. Okay, so with that in mind, we can now fill in the rest of these. We could say, well, if, were we on blue here? If 100 of them was 14, then wouldn't half of that be 50, which would have to be 7 centimeters? And then when we pull that, this would be 28. Do you see how we're using proportional reasoning again? Okay, so we can go in either direction. If we have the number of centimeters, we can multiply that times 7 to get the number of pennies. And if we have the number of pennies, we can divide by 7 to figure out the height in centimeters of that penny tower. All right, so now it is time to answer the big question. How tall would a tower of 1 million pennies be? Once again, when we know the number of pennies, we divide it by 7. So go ahead, work through that process. It would be good for you to practice the division algorithm, although I know many of you will just jump right to the calculator, and that's not a horrible idea to go straight to the calculator, especially in a situation with this where you got so many zeros you got to worry about. But I'm going to just do it anyway. You can watch me do it. You can grab your calculator, figure out what the answer is, and declare your answer. But I'm going to work through the process. So let me give myself plenty of room down here because this is going to be a big, long tail on this. 7 goes into 1 0 times. It goes into 10 one time, and that was 7. Remainder of 3. Bring down the next digit, which is a 0. Please make sure when you are doing this, I cannot stress this enough, make sure that you're keeping everything straight. When you start wrapping this guy and making a little map of Mexico here out of your division problem, it's going to be really tough to line everything up and make sure you get a correct answer. So make sure those are straight down. What was our next one? It was was it 4? Because 4 times 7 was 28. Gave us a remainder of 2. Bring this down. That was a 2. What was that? 14. So that gives us 60. Bring down the next one. 7 goes in there. 7 times 9 is 63. So this must be an 8. I think there's a comma belongs there. And that would give us 56. Bring down the next 0. That's going to be 5 for 35. Bring down the next 0, and that's going to be a 7 for 49. And this is never, ever going to terminate. Because look, we're going to start all over again. We're going to get 1 here again. Then we're going to get a 4, then a 2, then an 8, then a 5, and a 7. And if you see this on the calculator, clear out 1 million divided by 7. See how it's repeating digits? The 142,857, 142,857, 142. It round it there. My calculator on this computer automatically rounds. But so yeah, we're just going to round this to the nearest centimeter. So here we are. We can declare our answer. A 1 million penny tower measures 142,857 centimeters. Okay, so maybe you didn't want to go through and do all that division. Maybe you wanted to use proportional reasoning instead, since we knew that 1 centimeter was equal to 7 pennies. And we knew that 100 pennies was approximately 14, but really I think it was close to 14.3. So maybe I'll just go ahead. Let's keep it at 14. We'll just keep it simple as possible. Although let me just tell you, the more times you round things, the less accurate your answer gets. So, doing it this way gave us a very specific answer, whereas you're going to see where we round off and use proportional reasoning, sometimes that's going to affect our accuracy. So let's answer these questions here. How many groups of 100 pennies are there in 1,000 pennies? So if you had stacks of 100 pennies, how many of those stacks would you need to get to 1,000? If you said 10, you got that correct. 10 times 100 gives you 1,000. And how many thousands can you fit into a million? Are you going to count on your fingers for that one? Or do a little bit of mental math? What do you multiply times 1,000 to give you 10,000? What do you multiply times 1,000 to give you 100,000? So what are you going to multiply times 1,000 to give you a million? Well, turns out that's 1,000 thousands is the same as a million. So now work on your own. You don't have your team there to figure out how many towers of 100 pennies it would take to build a tower of 1 million pennies. So if there are 10 here and 1,000 here, right? 10 of those go into 1,000 and 1,000 thousands go into a million. How many total towers would that be? Give you enough time? Pause if you need more time, because I'm going to show the answer. That would be a total of 10,000 towers. So if every tower has 14 centimeters, we multiply 14 times 10,000, that means it's going to be rounded off, of course, to 140,000 centimeters. Now, how close does that come to our answer here when we did the division? Remember, we rounded off to 14 instead of having it be 14.2857. So it's a little less accurate. We rounded down. 140,000 compared to 142,000, pretty close. So we can declare our answer as a number of centimeters. But maybe when you made your prediction, maybe you didn't think in terms of centimeters, maybe you thought in terms of meters. So if you said about 1,400 meters, since there are 100 centimeters in every meter, divide this by 100, and you get 1,400, and there are 1,000 meters in every centimeter, in every kilometer, so that would give us a tower that is 1.4 kilometers tall. Pretty close to a mile. All right, so if that's the case, Anouk wants to compare, this isn't really an assessment, just something for us to think about. Anouk wants to compare the Million Penny Tower to the height of Mount Everest. She read on the internet that Mount Everest is approximately 8,848 meters tall. So, with that being the case, which is taller? Looks like Mount Everest is almost 9,000 meters tall, and the Million Penny Tower is 1,400 meters. So how many of these can you fit into 8,848? I will use my calculator for this. 8,848 divided by 1,400 means Mount Everest would be like between 6 and 7 million penny towers. If I actually didn't round, well, let's take it to 1,400. No, hold on. 8,848 and divide that by 1,430, which would be if we rounded it up to 14.3 instead of 14. It's still about 6. So yeah, let's estimate that Mount Everest is about 6 times the height of our Million Penny Tower. All right, so that just gives you a practical kind of a way of thinking about proportional reasoning. Doing investigations is often a strategy that mathematicians will use to solve problems that otherwise seem sort of complicated. So here was an example of us taking pennies and a ruler and answering a pretty complex problem. So, good luck on your homework. Did we make it below 25 minutes? Yes, we did. Good job. All right, and I will talk to you soon. Take care. Bye.
Hey, feeling good, like I should.